Today we're looking at the Physics AS Unit 2 paper from CCEA, the 2016 one from June, and it's Waves, Photons and Medical. Question 3. An object OA is placed on the principal axis of a lens as shown in figure 3.1. This lens produces an upright and diminished image. The positions of the principal focus F and the optical center C of the lens have been marked. So whatever's going on here with this object, a lens here produces an upright and diminished image. Now, a converging lens can produce a diminished image, but it's an inverted diminished image. So an upright diminished image must be a diverging lens. So that's really what we're meant to recognize here. So we're asked now to complete this diagram by drawing and labeling the type of lens used, by drawing two rays to help us locate the image, and by labeling the image IB and indicating whether it is real or virtual. So you could introduce a diverging lens by drawing this sort of apple core shape, but the standard way to do this is to use a vertical line with arrowheads pointing inverted. I'll show you what I mean. So you draw a vertical line along the optical center to show where the object, the lens, is going to be, and then you use these inverted arrowheads to show that it's that type of lens. So a converging has normal arrowheads and a diverging has these reversed arrowheads to show the sort of, shape difference between that kind of lens and that kind of lens, if you see what I mean. So now we have to add some rays to this going from the top of the object here. One will pass through the optical center and keep going. One will pass through this lens and diverge as if it came from the focal point here. So those are the two rays we need to add. So we add this ray down through the optical center and another one which is parallel to the axis. Now it's this second ray that helps us to figure out where the image appears to be, because it will appear to have come from this focal point. And so if we dot this back behind the lens, we can find this common point just here, where these two leaving rays appear to come from. So the arrows show the path of the actual light travelling through this lens, and it diverges after leaving the lens, but this particular ray here to an observer would appear to be coming from some point down here, and so we find that the common point that any observer on the outside thinks this light's coming from is actually here. So that'll be the top of the image. So we want to put in an image arrow there. That's where our image is. And so we were told to label it IB. The object here was labeled OA, object going all the way up to A. So the image goes all the way up to point B. Now you can see this is behind the lens here, and so we would describe that as a virtual image. So at this point we just add our labels and tidy up our diagram. And that's it. Part B. A student carried out an experiment to determine the focal length of a converging lens. She obtained a series of U and V values and recorded these in a table with headings as shown in Table 3.1. So we've got U, object distance there in meters, V, image distance in meters. Draw a labeled diagram of the equipment that the student used to obtain a set of results. Clearly identify the measurements U and V on your diagram. So we're using a converging lens here, and we're meant to get sets of U and V values. So U is how far you set the object in front of the lens, and V is where the distance from the lens to where you would find a sharp image. So we will need a system that will allow us to set up an illuminated object, like some kind of light bulb crosswires kind of thing, a position for the lens to go in between, and then some screen on the other side to pick up where we will get a sharp image. So we set up some kind of illuminated object here with a lamp, and the idea is that the light will come out through this little crosswire here that we can then focus at the other side. So we'll obviously also need our lens, and there would also be some kind of meter stick involved for measuring the distances. There'll be lens somewhere between the illuminated object and some screen that we're going to have to add over here. So we'll set this up. There'll be an object distance here, there'll be an image distance here, and the image distance is specifically when we get a sharp image formed on the screen. So you'll want to put a center line on the lens and confirm absolutely that you're measuring all the way to that center line. And the same on the other side where you're measuring V, you're going to want to go all the way to that center line on all the way to your image. So just put some labels in to try and clarify what it is that you're doing. Part 2. The student plots a graph of U plus V against UV and obtains the graph shown in figure 3.2. Explain how she would obtain the focal length of the lens from this graph. Now, those of you who've used shortcuts with the resistor, when resistors are in parallel, the 1 over R1 plus 1 over R2 equals 1 over R total, that equation is very similar to this, and there is a little shortcut related to that. Okay, so we need to just think a little bit about the resistor equation, or the lens equation, and how that relates here. So we've got that 1 over U plus 1 over V equals 1 over F. Well, if we take that left hand side and try and simplify it, we would have to take a common denominator of UV. Now, that being the case, then the first term, 1 over U, would have to be V, because V over VU, the V's would cancel and you would get 1 over U. And the other term, the 1 over V term, would have to be U. So that's what would equal 1 over F. The sum of U and V over the product of U and V. So how would this relate to what they plotted? Well, what they plotted is the sum of U and V, which is this top line. So they plotted U plus V on the y-axis, so we'll put that on its own. And so we need to get the other stuff together, and it would be 1 over F times UV. So this is now in the form of y equals mx, because this is what they're plotting on the x here. This is what they're plotting on the y. So the gradient must be this thing. And so the gradient of this graph would have to be 1 over F. And so the focal length would be 1 over the gradient of this graph. Question 4a, state the principle of superposition. So this is like straight from your notes. need to talk about what happens when two waves meet. So when they meet and combine, the total displacement at any point is the vector sum of the individual displacements at that point. So that's just straight book work. That's the kind of thing that you've written a nice, clearly, tightly defined definition and you've learned it off. So nice easy marks there. So two waves meet and combine, the total displacement at any point is the vector sum of the individual displacements at that point. So now we're given a little pair of waves to work on. So figure 4.4 shows the displacement of two waves W1, W2, which have different amplitudes and frequencies. Use the principle of superposition to draw the resultant of these two waves onto figure 4.1. So we use this vector sum thing. So what I'm going to do is take the vectors belonging to the dotted line and add them to the solid line. Okay, so at the start here we have nothing plus this little vector, which will leave us exactly at the end there. At this next point we're adding nothing, so that'll put us there. At this next point we have a vector that's that way, and so that'll have to be added up here. 1 square worth. Here we have 0 plus 0, that's fine. Here we have an upward vector, sorry, and so that'll have to be added 1 square down here. And here we have nothing being added to this, so that'll bring us to there. And here we have a negative vector being added to another one, which will bring us to about there. Here we have a vector like this being added, so that'll bring us to about there. And then last of all, we have nothing being added, so that'll bring us to about here. So I have to find the tips of all of my vectors. So I'm going to come in with another color and just clarify where I need to be plotting to. So here, here, because there's nothing being added. Here we have a downward thing added to the solid line. Here we have nothing added to the solid line. Here we have an upward thing added to the solid line. Here we have nothing added to the solid line, and here we have a downward added to another downward. Here we have the solid line plus a downward, and eventually this last part we have nothing being added to the solid line. So now we have to plot through these green dots, and I get something like that. So hopefully you can see what I was doing there. Upward added to the solid, nothing added to the solid, downward added to the solid, nothing added to the solid, upward added to the solid, nothing added to the solid, downward added to the solid, downward added to the solid, and then nothing added to the solid. So you find the locations of adding the dotted vectors to the solid line values. Okay. The following experiment, known as Meld's experiment, can be used to demonstrate standing waves on a string. The apparatus is used is shown in figure 4.2. The mass is attached to a string, and this keeps the string taut. A signal generator is connected to the mechanical oscillator, which causes a progressive transverse wave to be sent along the string. This wave is reflected at the pulley, and a standing wave can be observed at certain frequencies. The frequency of the signal generator slowly increased from 0. The fundamental mode of vibration is observed when the signal generator is set to 56 Hz. Calculate the length of the string, big L, if the speed of the transverse wave in the string is 106.4 meters per second. So the first thing to recognize is that when there's a vibration between these two positions, which are big L apart, if this is the fundamental vibration, then it'll be like that and like that. And so at this point, L is like half a lambda. Remember, lambda would be for a whole cycle, but we've only got half a cycle in the picture, and so L is going to be lambda over 2. And that means that lambda is going to be 2L. So from the point of view of the wave equation, we have a frequency of 56 Hertz, and we have a wave speed of 106.4 meters per second, and we can get a lambda from that. So lambda is V over F, which is going to be 106.4 over 56. And L is going to be 106.4 over 2 times 56, which gives us an L of about 0.95 of a meter. Part 2, the frequency then of the signal generator is increased until it reads 168 Hertz, and another standing wave is obtained. Determine the standing wave pattern obtained, and sketch this on figure 4.3. So we've got the F0 at 56 Hertz, and we want to recognize that this frequency is 3 times F0. So at this frequency we're going to get 3 bumps of standing waves, and so we need to divide it up into 3 so that we can draw the pattern that we would get. Obviously draw it a bit neater than I've done there. So this is the pattern for 3 times the fundamental frequency. We get 3 bumps of antinodes. It says on your sketch, mark a node and an antinode. So the antinode is going to be at these bumps where the maximum vibration occurs. Nodes are the places where 0 vibration occurs. And that concludes our working of questions 3 and 4. Thanks for watching.